Greetings of the day. I Asha K, Assistant Professor, Sai Vidya Institute of Technology, going to present in today's class DSP Algorithm and Architecture 7th Semester Elective Course 17 EC 751. Now we will discuss about the Module 3, the topic called as On-Chip Peripherals. We have here the on-chip peripherals used to facilitate the interfacing with the external devices. We have the peripherals such as general purpose input-output pins, a software programmable wait state generator, hardware timer, host port interface. We'll be having here a clock generator as the peripheral and also serial port as the one of the on-chip peripheral of the TMS 320 C54XX processor. The another important peripheral which is present on the processor are clock generator. The clock generator on TMS 320 C54XX device has two options. The one option that we are having here is an external clock signal and an internal clock signal. In the case of external clock option, a clock source is directly connected to the device. Whereas in the internal clock source option, it uses an internal clock generator and a phase locked loop circuit. This phase locked loop circuit in turn can be an hardware configured or a software programmed. All the devices of TMS 320C54XX family processor will not have this kind of clock option. The clock and the operating frequency of the processor will vary from one device to the other device. So this is the brief explanation about the clock generator present in the TMS 32054XX processor. The next topic in the peripherals we have here is serial input-output ports. We have basically three types of serial ports available in the TMS processor. The first one is synchronous port, the second one is buffered port, the third one is time division multiplexed ports. The synchronous serial ports are high speed full duplex port and that provide direct communication with serial devices such as coder and decoder and analog to digital converter. The second one we have here is the buffered serial port is synchronous serial port that is provided with an auto buffering unit and is clocked at the full clock rate. The head of servicing the interrupts is based upon this buffered serial port. We have the third one, a time division multiplexed serial port. It is a synchronous serial port that is provided to allow the time division multiplexing of the data. The functioning of each of these on-chip peripherals is controlled by the memory mapped register assigned to the respective peripherals. Now let us discuss about the interrupts of TMS 320C54XX processor. Many a times when a CPU is in the midst of executing a program, a peripheral device may require a service from the central processing unit. In such situation, what happens? The main program may be interrupted by a signal generated by the peripheral device. This results in the processor suspending the main program in order to execute another program which is called as with the help of an interrupt service routine to service the peripheral device. Upon completion of the interrupt service routine, the processor returns to the main program to continue from where it is left. The best example of interrupts are when we are taking a class, if any important circulars comes from the HOD or the principal, definitely the professor who is handling the class will interrupt the class, given highest priority to those circulars, and those circulars will be read in the class. If other than that, if highest priority is not required, then what we do, we'll continue with our normal execution of the program or normal process of teaching in the classroom. The interrupts may be generated either by internal or external device. It may also be generated by software. So here, not all the interrupts are serviced when they occur. Whenever we wanted to give the priority, we'll give the priority to those interrupts. If priority is not required, we'll not execute those interrupts. Only those interrupts that are called non-maskable are serviced when they occur. Say any important circular from the higher authorities, definitely we will read that in the class. If other than that, if any extra things will appear to the class, so we'll not consider that. We'll keep it with us and we will read at the end or later that will be conveyed. Other interrupts, which are called as maskable interrupts, are serviced only if they are enabled in the processor. There is also a priority to determine which interrupt gets serviced first if more than one interrupt occurs simultaneously. Here we'll be having 32 interrupts in the DSP processor. Some of these interrupts are reserved for the use by central processing unit. This is the brief explanation about the interrupts of TMS 320 C54XX processor. The next topic that we are going to discuss here is pipeline operation of TMS 320 C54XX processor. It consists of 6 different phases in the pipeline operation. First one we call it as prefetch phase. What it does in this phase is loads the PAB with the program counter's content. Afterwards, the instruction will move to the fetch phase. In the fetch phase, loads the PB, that is program bus, with the fetched instruction word. When the instruction moves to the decode stage, loads the instruction register with the content of the PB, decodes the instruction register content in the decoding phase. Whereas the fourth phase that we have here is loads access phase. It loads the data address bus with the data 1 read address if required, and also loads the data address bus with the data 2 read address if required. And also in the access phase, a very important thing is that auxiliary registers and stack pointers are updated. The fifth phase in the pipeline operation of TMS 320C54XX processor is read phase. In the read phase, it loads the DB data bus, CB data bus with the data 1 and data 2 read operands respectively. It also loads the EAB, that is address bus, address bus with the data 1 read address if required. And later the sixth stage or the phase we have here is execute and write. In execute phase, it executes the instruction and loads the EB with the write data. So these are the 6 different phases of pipeline operation of TMS320C54XX processor. You can remember with an acronym: prefetch phase, fetch phase, decode phase, access phase, read phase, and execute and write phase. So this PFDARE will help you to remember the pipeline operation of TMS320C54XX processor. Now let us discuss about the examples of pipeline operation. The first example: show the pipeline operation for the following sequence of instruction. If the initial value of the AR3 is 80 hexadecimal and the value stored in the memory location 80 hexadecimal, 81 hexadecimal, 82 hexadecimal are respectively 1, 2 and 3. Here it is 1, for this here it is 2 and for this here it is 3. The instruction set given here it is: load star AR3 plus content to accumulator, add immediate value 1000 hexadecimal to accumulator and store the content in the accumulator itself, and store lower word of the accumulator to AR3 plus. So to the AR3 plus location, the content of AR3 plus location is loaded with the accumulator lower word, that is from 0 to 15. So to perform this, let us analyze the 6 phases of the pipeline operation. The first one phase is prefetch, fetch, decode, access, read, execute and write operation. We have here the content of the AR3 and the content of the accumulator register. What is happening after each instruction execution in each phase? First one, during the clock cycle 1, the prefetch phase enters the load instruction enters to the prefetch phase, and again in the second phase it is fetched here, and again it is decoded here. Till here it is decoded. If you just observe, the content of the AR3 initially is 80 hexadecimal. It is retained as 80 hexadecimal and previous value of A was unknown. That's why it is declared as don't care. When the load instruction enters to the access phase, what happens? After execution of this, the accumulator is loaded with the content of the AR3. The content of the AR3 that I am having here, it is 1. Hence, that is loaded here. When it is loaded, the value of the accumulator is changed to 1. If I represent this in hexadecimal, this is 10001 hexadecimal. During this particular phase of operation, if you just see here, that is in the read phase, the data has been changed for the load instruction. In the access phase, the auxiliary registers will be updated. When auxiliary register is updated in the access phase, here initially 80 was the pointer which is pointing at 80, the AR3. Now AR3 is incremented to 81 hexadecimal. Now 81 hexadecimal is the new value of the AR3. Similarly, when the load instruction comes to execute and write stage, so we'll be having here 1 hexadecimal is changed to 0001 hexadecimal. This is our representation for the addition purpose. Similarly, analyze the add instruction which is in the prefetch phase, add instruction which is in the fetch phase, and add instruction now it has come to decode phase, and add instruction I'm adding here 1000 hexadecimal immediate value to accumulator. See, now it is in the access phase and here there is no auxiliary register involved here. So hence will not be having any operations. So when it comes to this particular phase, add phase, no changes. Now when there is no reading purpose here with respect to read operation is concerned, hence this particular instruction will not execute the read phase. It directly moves to execute and write phase. Now the 1000 hexadecimal is added with the content of the accumulator. Now the accumulator content is 0001 hexadecimal will be added with 1000 immediate value. After the execution of add is completed, I'll be having 1001 hexadecimal in the accumulator A register. Similarly, try to analyze the store lower word of the data instruction. It is now in the prefetch phase, it is in the fetch phase, it is in the decode phase. When it has come to access phase, what happens? The auxiliary registers updated. Where we have learned this? We have learned in the previous slide. In the access phase, the stack pointer and the auxiliary registers will be updated. Now, if you just see the instruction, store lower word of the accumulator, comma, AR3 plus. After storing the accumulator to that memory location, what we have to do here it is, we have to increment the AR3. Earlier it was 81, now incremented, now the new value is 82. So, in the access phase itself, the changes will occur to the auxiliary register incrementing. Later, when it comes to read phase, the data is read to the accumulator, and in execute and write phase, it will be written onto the certain memory address, that is AR3. Now, the 82 auxiliary register value that is pointing at 82 will have in the presently present in the auxiliary register, and the accumulator content after execution of the third instruction, the accumulator is added with the auxiliary register content, and auxiliary register contents itself is the destination. Now it consists of 1001 hexadecimal value. Now let us discuss about the example 2. It shows here the pipeline operation of the following sequence of instruction. If the initial value of AR1 and AR3 and accumulator are respectively 84, 81 and 1. The value stored in the memory location, that is 81 hexadecimal, 82, 83, 84 are 2, 3, 4 and 6. So we have here the set of instruction. The set of instruction that we have here are add star AR3 plus to accumulator. The accumulator now becomes accumulator plus star AR3. Later AR3 is incremented. Then load star AR plus 1 to temporary register. The temporary register is loaded with this particular content of star AR1. AR1 it is incremented later. We have the next one, MPY star AR3B. The content of star AR3 multiplied with temporary register, and the result is stored in the accumulator B. Later, add the content of accumulator A with accumulator B and store the result in the accumulator A. Now analyze the cycles along with the pipeline operation. First step, consider we have ADD star AR3 plus, comma A. So if you just observe here, the add instruction, it is undergone all the 6 phases: prefetch, fetch, decode, access, read and execute and write phase. Also asked a question in the problem such that we need to provide the values of the register AR3, AR1, temporary register and an accumulator register A after completion of each cycle. Say consider when add is in the prefetch phase, the content of the auxiliary register will have, that is, which is pointing at the address 81, the content which is present here, it is 2. Similarly, when add comes to the fetch phase, no changes in the AR3, no changes in the AR1 and accumulator also no changes, and initially the temporary register values also don't care. When it has come to decode phase, so here also there is no change in the auxiliary register is concerned, and also if the accumulator and the temporary register is concerned. When the add instruction appears to the access phase, what happens? The previous value of AR3 is incremented by 1. That is, now AR3 plus is equal to, that is, it's incremented AR3, that is 81 plus 1, that will become 82. And there is no modification with respect to 84 in AR1, hence it is as it is. And accumulator no changes as it is, and temporary register no changes as it is. When it appears to the read phase, because here we are involving the indirect addressing, we have here the register, auxiliary register AR3, the read operation will be executed for this add instruction. When it appears here, again this registers remains in the same state. When add instruction appears to the execute and write state, what happens in the execute and write state of the that pipeline operation? If you just observe here, what is happening here after the completion of this, the accumulator is added with the accumulator content with star AR3 content. Accumulator content is 1, star AR3 content is 2, 2 plus 1 addition is 3, hence the after adding the added result is stored in the accumulator, hence the accumulator now consists of, that is, A plus star AR3, that is equal to 3. And this completes the execution of the add instruction. Similarly, the load has come to prefetch phase, fetch phase, decoding phase. When it appears to the load phase, we are involving here star AR3, AR1 plus. The star AR1 plus, if you just observe here, when it is there in the load phase, now if you just see after execution of the load phase, the auxiliary register is changed to 85. The change in the auxiliary register, now it is 85, and here this star AR1 plus is copied into the temporary register. What is there? The AR1 is pointing at 84. The content present in 84 is 6, that is copied to a temporary register, that is T, when the load instruction is in the read phase itself. When it is appearing into the execute and write phase, no changes with this previous values. Whatever the previous values are there, those previous values are retained as it is. Let us come to the third instruction, multiply, which is there in the prefetch phase, fetch phase and decode phase. See, it is pipelining operation. When add is in the access phase, load will be in the decode phase and multiply will be in the fetch phase. Next add instruction we have, that will be in the prefetch phase. Now for this MPY, let's assume that it is there in the decode phase, and when it has appeared to the access phase, when it has appeared to the access phase, if you just see here, the star AR3 plus, now the content of the previous value of the AR2 pointer, AR3 pointer, it is changed to AR3. That is 82 is now changed to 83. So this is happening with respect to the access phase of the MPI is concerned. And in the read phase, we have here, when it is in the read phase, again there is no changes in the AR3, AR1, accumulator and temporary register. But when this instruction is executed, that is the content of AR3 is multiplied with the temporary register, and then again the result is stored in the accumulator register B. The content which is present in AR3, here we have here, if you just see, the content of AR3, that is which is present at 82 is 3 is multiplied with the temporary register content, that is 6. The answer in decimal we are going to get is 18 decimal. 6 3s are 18. When I convert this into hexadecimal, so we'll be having, that is 16 ones are 16, and we will be having the remainder 2, that is 1 to hexadecimal. So for this value 1 to hexadecimal, what we are going to do here, it is add the content of the B register with the content of the accumulator and store the result in the accumulator. So when the accumulator, that is add instruction, is executed, if you just observe, when add instruction has come to read phase, no changes in the AR3, AR1, accumulator and temporary register. When the add operation has come to execute and write phase, now the 3 has been changed to 15. How it has been changed? Because of the addition of, that is A plus B, and stored into the accumulator A, 12 hexadecimal is added with 3 hexadecimal. The final answer that we are going to get here is the 15 hexadecimal, and 15 hexadecimal is stored in the accumulator A register. So this is the 6 different phases of pipeline operation of TMS 320C54XX processor. To prepare the content in this particular presentation, the textbook referred is this, and the reference books referred are the following. Thank you all.